right, so yesterday we were talking about this concept of continuity, and I want you to think about continuity as being able to draw a graph without lifting up your pencil, but we're going to explore a more mathematical definition of that, like what characteristics should we be analyzing either on a graph or from an equation to help us determine whether we can draw it without lifting up our pencil. So we left off yesterday kind of categorizing or identifying the different types of discontinuities on these four graphs. We're going to take a look at these four graphs a little bit more in depth today. So what I need you to do is be able to reference this page 74, but also be able to see this page 75. You need to be able to see two pieces of paper on your desk. Can you guys do that? Okay? Because if you take a look on page 75, we're going to first focus on the f of x function, which corresponds to the f of x graph on the previous page. So we're going to have to bounce kind of back and forth between graph and questions. Okay? So from yesterday, what type of discontinuity did we identify on that f of x graph? Go ahead, Sarah. A jump. And did we say where it was? At x equals 3. Okay, so not only can we classify the type, but we can give the exact location where that is happening. Okay? If you were to either take a look at the graph of f of x, or maybe even the equations, okay, the piecewise function, can we determine if f of x is defined? Meaning, is there a point at this x value of 3? Take a look at the graph or the equations. How can you determine if there's a point or not? What do you think, Tori?
There isn't, because in the side of the equation, whatever it's called,
Uh-huh.
it doesn't equal to something with the less than.
Perfect. Okay, so based off the equations, we can determine that there's no point at 3, because notice how in either domain section, there's no equal bar. Okay, you'll never ever equal 3. How can you tell based off the graph that there's no point at 3? Yeah. They're both open circles. Okay, so notice how depending on what information you know, you could determine whether you have a point or not. Okay, so we'll say no because we have no closed circle or maybe equal bar in the equations, depending on what you want to look at, either the graph or the equations. Okay. The next question is asking us, by investigating the constraints, aka the domains of the equations, where does the first piece end and the second piece begin? So take a look at your equations, okay, this domain or constraint section. Where does the first function end and the second one begin in terms of their x values? What do you think, Tori? You mean positive?
Yeah.
Positive. Okay, so notice how based off the first domain, the first equation starts at -8, but it ends at 3. And at that 3 value, that's where the second one picks up. Okay, so the first one's ending at 3, whereas the second one is beginning at 3. So this is really our point of interest on this graph, because if we're analyzing continuity, aka being able to draw a graph without lifting up your pencil, if you have one piece ending and another one beginning, don't they have to kind of match up in order for you to be able to draw it without lifting up your pencil? Okay, so we're really interested in this location, okay, where one piece ends and the other one begins. So let's take a look at this x location of 3 a little bit further. If you were to approach that 3 value from the left, okay, so graphically, here's that x value of 3. If you were to trace the graph towards that 3 location from the left-hand side, what y value is your graph getting closer to? Yeah, we're getting closer to 2. I don't care if there's an open circle there. I don't care if there's a closed circle there. I'm just concerned with what is the y value we're getting closer to. Let's do the same thing, but from the right-hand side. Okay, so on the graph, if we were to trace the right piece towards that x location of 3, what height are you getting closer to? Yeah, we're getting closer to 4. All right, so we can figure out what the left side of the graph is doing and what the right side of the graph is doing looking at a picture, okay, looking at a graph. But let's say we didn't have the graph. Okay, we're going to kind of step it up a bit. How could we still get the same value of 2 or 4 if we didn't have a picture? Yeah.
Use x equals 3 and put the 3 into the x's of the equation.
All right, let's go ahead and take a look at the equations. Okay, so we're trying to approach this value of 3. Let's go ahead and use the left equation, which would be the first one, and then the right equation, which would be the second one. So let's see, as x approaches 3 from the left, we're going to plug in this value of 3 into the first equation, which is that absolute value. Let's see, 3 plus 3 is 6. Absolute value of 6 is still 6. Minus 4 is 2. And notice how that matches what we said based off the graph. Let's check the right-hand side, which would be the second equation. If we plug in 3, negative 1/3 times 3, we got negative 1, plus 5, we get 4, which matches what we said based off the graph, right? So even if we didn't have a picture, a graph, we could still determine what the left side is doing and what the right side is doing, okay, using those equations to help us. So at the very beginning, we said that there should be a jump based off the graph because we saw that yesterday. But how are these numbers perhaps confirming that idea? Can you explain what this is telling us? Yeah.
If it was a constant, it was 200
All right. So if they were, what do you mean by constant? If they were, is that what you said, constant?
I said
A continuity. Okay, so if it was continuous, okay, these numbers would be exactly the same because where one equation ends in terms of its height should be exactly the same where the other one begins in terms of its height. Okay, they're matching up. But notice how this height is 2, whereas this height is 4. Those are not going to match up. Okay, they're at 2 different levels. Okay, so we'll say that this graph is discontinuous at this x value of 3. Okay, that's our special location where one graph ended and the other one began, because the left and right sides do not meet. That's what's causing the jump. They're at 2 different levels. Okay, they're not meeting up. Does that make sense? All right, so we're going to go through the other graphs today, the g of x, h of x, p of x. Make sure you can reference those graphs on the other page. Okay, let's take a look at the g of 1 next, which is the upper or the other right one we have. Okay, this one in the top right corner. From yesterday, what did we say was going on that graph? What type? Yeah. Another jump. And where was it located? Yeah. -3. Okay, so either based off the graph or based off the equations, is there a point at that -3 location? Tori? All right, so it's yes, and we would say, let's see, if we were to plug in -3, we would get out -2. Okay, if you take a look at the graph, there's a closed circle, which means that point is defined. Okay, so graphically speaking, maybe we'll label this as a closed circle. All right, let's take a look at the equations from the g of x graph. Where does the first equation end and the second one begin? Where's this special location that we need to kind of analyze or look into? Now it's negative 3. There you go. Okay. So let's take a look at this location a little bit further. What's happening to the left of negative 3? What's happening to the right of negative 3? Okay, so take a look at your graph. Find that negative 3 location on X. If you trace the left-hand graph, looks like you're getting closer to a height of negative 2. And if you trace the right-handed graph, looks like you're getting closer to a height of negative 4. Again, open circle, closed circle doesn't matter. Okay, we're just concerned with what are we getting closer to. All right. So these numbers are nice to find based off of a graph, but let's make sure we can still find them even if we didn't have a graph. So let's take a look at the equations. As x approaches negative 3 from the left, which equation would we use to help us find the left side? See, take a look at your equations at the top. Which one shows up to the left of negative 3? Yeah, the top one, yep. If you think about numbers to the left of negative 3, like negative 4, negative 5, negative 6, those are all falling within that domain. So we're going to plug in negative 3 into that first equation. Now graphically, we already said we should get negative 2, but let's make sure we can actually do that. Negative 3 plus 6 is 3, 3 squared is 9, negative out front is negative 9, plus 7, we get negative 2. So it checks out. Let's go ahead and take a look at the right-hand side of negative 3. Which would be the second equation, or the only other one that's left. Okay. So negative 3 plus 3 is 0, square root of 0 is still 0, negative 0 is still 0, minus 4, so we're left with negative 4. Notice how it matches. So either based off of a graph or an equation, we can figure out left or right-hand side. Okay, so at the very beginning, we said it was a jump. How are the numbers confirming that idea? What's going on? Let's see, discontinuous at the x value of negative 3 because why? Yeah. The points don't meet. Okay, so the left point or side does not meet the right point or side. Again, that's what's causing the jump. If one side has a different height than the other side, they're not meeting up. Okay, we have that jump going on. We doing okay? All right, let's go ahead and flip to page 76, okay, but we still need to reference the other graphs, okay, so you might have to pull out some papers. This time we're going to take a look at h of x, which is the bottom left-hand graph. From yesterday, what kind of discontinuity did we have? Yeah. Whole at x equals negative 1, okay? So is there an actual point at that negative 1 location? Yeah. No, because we have an open circle, or based off the equations, you could say there's no equal bar. Okay, we'll never actually equal negative 1. Okay, however you want to phrase it. So take a look at the equations. Where does the first piece end and the second one begin? Where's this special location we need to analyze? Yeah. Negative 1. Okay. So let's take a look at this a little further. We're going to trace negative 1 from the left, and negative 1 from the right, we're going to take a look at the heights. Okay, so let's find negative 1 on the graph. And if we trace the left-hand side, looks like we're getting closer to a height of 1. And if we trace the right-hand side, we're also getting to a height of 1. Are we okay with that idea? Can we trace a graph from the left and the right? That's actually a calculus concept. Okay, my calculus kids are doing that right now. Do you think we can handle that? Good. Okay, so let's see if we can get those same numbers based off the equation, just in case we didn't have a graph. As x approaches negative 1 from the left, which equation represents the left-hand side of negative 1? Good, Marie? The first one. Okay, so let's plug in negative 1 into the first equation. Negative 1 plus 4 is 3. Absolute value of 3 is still 3. Bless you. Minus 2 is 1. Notice how it matches. Let's go ahead and check the right-hand side, which would be the other equation. If we plug in negative 1, negative 1 minus 1 is negative 2. Negative 2 squared, though, is a positive 4. We have a negative out front that's going to change it back to a negative 4. Plus 5 would give us 1. Okay, so notice how it's checking out. So why do you think these numbers are telling us that we have a hole or a point discontinuity? What do you think?
It was going to be the same place, but there's no closer.
There you go. Okay, notice how the left and the right are meeting up. Okay, they are approaching the same height, but unfortunately, where they meet up is an open circle, which means you'd have to lift up your pencil if you were drawing that graph. Okay, so we'll say discontinuous at the x value of negative 1 because the two sides, aka left and right, meet at an open circle. Can we see that based off the analysis? They're going to meet up, but we said up here that there was no point there. Okay, aka open circle. So that's what's giving us the hole. Let's check out our last one of P. Okay, what type of discontinuity did we say P had yesterday? And where? Yeah. Hole at negative 3. Okay. Is there a point somewhere at negative 3? Either based off the equations or the graph? Anthony's shaking his head yes. Maybe we can find it. If you were to plug in negative 3, what would you get out? Let's take a look at the graph. Go ahead, Marie. Okay, so based off the graph, the closed circle's at negative 2. Based off the equations, the only one that could equal negative 3 is the middle one. And notice how that has a value of negative 2 as well. Okay, so both of them are checking out. So this is a closed circle on our graph. Where's this special location that we're concerned with? Where does the one function end where the other one begins? Good, Marie? It's at that negative 3. Yep. So let's take a look at this a little bit further. We're going to trace the graph from the left and the right to see what's happening. So graphically, let's find negative 3. If you trace the left graph, looks like you're getting closer to a height of 2. And if you trace the right side, you're also getting closer to a height of 2. Let's make sure we can get those same values based off the equations, okay, just in case we didn't have a graph. So as x approaches -3 from the left, which equation are we going to use to represent the left-hand side of -3? Good, Marie? The third one. Or this one, the bottom one? Okay, so if you think about numbers to the left of -3 on a number line, that's like -4, -5, -6. Which one of the domains would those numbers fall in? -4, -5, -6. Are those less than -3 or greater than -3? Yeah, they're less than. Okay, so we're going to use the first equation. Let's go ahead and plug in -3 there. All right, 1/3 times -3, we got -1. Then plus 3 would give us 2. Checks out. Let's go ahead and check the right-hand side of -3. On a number line, if you think about numbers to the right of -3, like 0, 1, 5, okay, where would those numbers fall within our domains? This one's a little tricky because technically we have 3 pieces. We got to figure out which one's to the right-hand side. Which one are we going to use? Yeah. The bottom one, greater than -3. Okay, so let's go ahead and plug in -3 into that equation. -3 minus 1, we got -4. Absolute value changes it to a +4. Minus 2, we'll get 2. All right, checks out. So what are all these numbers telling us? We said we should have a hole because we saw the graph yesterday. But if we didn't have a graph, how are these numbers confirming that idea? What do you think? We can say discontinuous at the x value of -3 because why? What's going on? Yeah. How do you know it was open? Up here we said it was closed though. It doesn't match. Okay, notice how the two sides are meeting up. Okay, they're both approaching 2, but there is not a closed circle at this same spot. Yes, we have a closed circle on the graph, but notice how it's at a different height. It's a different spot. So if the two sides are meeting up, but the point is somewhere down here, okay, wouldn't that cause an open circle to be in the middle where they're meeting up? Okay, so you got to look at the numbers and kind of analyze, think about a graph. What would this look like, just in case you didn't have one? So we'll say because the two sides meet at an open circle. Okay, we did have a closed circle, but it's not at the point where the sides are meeting. Okay, that's a little tricky. We think we get that idea? Okay, the two sides have to meet, and there must be a closed circle at that point where they meet. Okay, so we're going to use that definition for continuity on the next page. Okay, on page 77. All right, so let's formally define continuity. You can think about it as drawing a graph without lifting up your pencil, but mathematically, we have to have two sides meeting at a closed circle. So we'll say a graph is continuous at some x value. Okay, sometimes we use x equals a. Only if the left and right sides meet at a closed circle. All right, so if that's not happening, we've seen two different types of discontinuities. Okay, we have a jump or a point. What we're going to do is classify those two different ideas. Okay, let's say we didn't have a graph. what should we be looking at in terms of the numbers or the analysis to help us figure out which type of discontinuity it is. So in a jump, we saw two different types that we could have. We could have a jump discontinuity with two open circles. Maybe we have a jump discontinuity with one open, one closed. Okay. For a point discontinuity, or a hole, whatever you want to say, we had two options there as well. Maybe we had a graph connecting at an open circle, but we also had an example, okay, the last graph we just did, we had 2 points connecting, but didn't we have a closed circle somewhere else? It just wasn't where the lines were meeting. So there could be perhaps a closed circle either above or below the hole. In either one of these cases, you still have a hole, okay, in your graph where you'd have to lift up your pencil. Okay, so graphically speaking, we have these two types of jumps or these two types of holes. Okay, so in terms of the numbers, the analysis, we said for a jump discontinuity, the two sides do not meet at the same height. But if you look at the two options here, notice how we may have a closed circle there on the graph, but we may not. Okay, so we'll also maybe classify, we'll maybe say, maybe there is a point, aka closed circle. There may be one or they may not be one. That's not affecting whether there's a jump. Okay, the whole idea of a jump is the two sides don't meet up. If there's a closed circle there or if there's not, has no effect on that. Okay, notice how in either one of these cases they're still not meeting up. Okay. For the point discontinuity though, the two sides do meet at the same height. But the same thing's kind of going on here. Maybe we have a closed circle at a different height, or maybe we don't have a closed circle at all. So we'll say maybe there is a point, maybe there's not. So the real kicker is, what are the two sides doing? Okay, are they meeting at different heights, aka a jump? Or are they meeting up at an open circle somewhere? Okay, that would give us that hole. Is it starting to click a little bit? Okay, we're going to amp it up though, because if you take a look at the next example, notice how there's no graph. Okay, so no more picture. We're just going to have to go off the equations. Okay, so let's take a look at this first. For each of the functions below, determine the value or values at which the graph could be discontinuous. So can we figure out, based off this equation, where that special location is where a jump or a hole might be? What do you think? How'd you know? So notice how -1 is the location where the first one ends and the second one begins. Okay, we want to make sure that they're meeting up, because if they don't, that's a jump. If they do meet up, that's good, but we got to make sure there's a closed circle there too. Okay, so we're going to check that x value of -1. Let's go ahead and see if we have a point. Okay, can you plug in -1 into either equation? How can you tell? Yeah. All right, so we'll say no point because there's no equal bar on either one of those for -1. So if there's no point, we automatically know that there's an open circle. Graphically speaking, even though we don't have a picture. Bless you. Okay, so now we got to check out the sides. Okay, so we know there's an open circle. If the sides are meeting up at an open circle, we know it's a hole. But if the sides are not meeting up, okay, we have some type of jump that has the two open circles because we said there's no point there. Okay, so let's go ahead and check out the sides. So we got to check the left and the right. As x approaches -1 from the left, which equation are we going to use? Yeah. The first one. Okay, so let's plug in -1 into the first equation. -1 plus 4, we got 3. 3 squared is 9. Negative out front becomes -9. Plus 3, we have -6. Let's go ahead and check out the right-hand side of -1. That would be the other equation we haven't used yet. Okay. So -1 minus 3, we got -4. Absolute value changes it to +4. Minus 10 would give us a -6. So what is this analysis telling us? There's no graph. Go ahead, Marie.
It's a point discontinuity.
A point, aka a hole. Why? Go ahead.
Because they technically be the same point, but it's open circle.
Okay, notice how the left and the right-hand side are meeting up. Okay, they are approaching each other, but the moment that they would meet, there is an open circle. Okay, so we'll say a hole at the x value of -1. Because left and right meet at an open circle. You see how we described the discontinuity even though we didn't have a graph? Okay, it's all based off of those equations. Let's go ahead and try the next one. Okay, where is this special location that we have to check? Where does one equation end and the other one begin? Yeah, it's -1 again, okay? So let's see if there's a point at -1, aka a closed circle. Can we plug in -1 anywhere? Yeah.
Yes.
All right, so yes, we have a point. And if we were to plug in -1, okay, we would have to plug it into the second equation because that's where the equal bar is. So let's go ahead and plug it in to see where this closed circle is located. All right, -1 plus 3, we got 2. Absolute value of 2 is still 2. Minus 4, we got -2. Okay, so we have a closed circle at -2. But that's not really telling us anything because if you take a look at the chart at the top, we could have a closed circle for a jump. We could have a closed circle for a point or a hole, okay? So we got to analyze what's going on both sides. Okay, as x approaches -1 from the left, which equation would we use to represent the left-hand side? Good, Marie? The first one. Okay, so let's plug in -1 into the first equation. All right, -1 plus 3 is 2. Absolute value of 2 is still 2. Times the -2 out front, we got -4. Plus 2 is -2. So it looks like the left-hand side of this graph actually has a closed circle on the end of it. Okay, notice how those values are the same. Let's go ahead and check out the right-hand side of -1. That would be our second equation. Do we already know what we're going to get out? Did we already plug in -1 into that guy? Didn't we do that for the point? Okay, so without a graph, what are all these numbers telling us? Are we continuous, or do we have a jump or hole? What do you think?
We'll continue.
How do you know?
Because although the first equation is an open circle, we still meet at a closed one.
We still meet at a closed one. Okay, so notice how if you look at the domain pieces, the first equation is ending at an open circle, but the second one is filling in that open circle, because don't you have that equal bar? Notice how the left and the side are meeting up. They have the same height, and they're specifically going to meet at that closed circle. Okay, all the values are the same, meaning you're going to be able to draw the graph without lifting up your pencil. So we can say we're continuous at the x value of -1. Because the two sides meet at a closed circle. We doing okay? Making sense? We amped it up. We didn't have a graph this time. We just had the equations. Okay? We're going to save the back page for tomorrow. Okay? We're going to amp it up even more. Take a look at how we have some 3 equations. I'll let you guys have a rest over the weekend. Deal? All right.